Hello everyone, I'm introducing to you today our work on leveraging structured metadata for improving web question answering. And this work was done during my internship at Microsoft Research. And it's a work. And so what is the task that we're tackling for web question answering? Given a question like this, how do we cook something for how long? Then we first retrieve the candidate passages from a bunch of websites. And then we select the best candidate from all the candidate passages. And in this case, it is the second one. And what we are tackling in this paper is answer passage selection. And from the statistics reported from the semantic org projects, we know that there is a large portion of websites contain metadata annotations that provides a deeper understanding of the content. For example, here, there's a recipe from the simply recipes.com website about classic meatloaf. And from the HTML file for this corresponding text, we know that many of them are decorated with predicates, like with a hierarchy from the semantic org projects. Like, for example, here, the preparation time, 20 minutes, is decorated by prep time recipe predicates. And we ask a question here if we can utilize this additional information from the HTML files and how do we leverage this metadata information for better web question answering. And our proposal here, or say investigations here, is to firstly generate metadata decorated passages. And as you can see, given the textual objects and predicate pairs, we firstly decorate the raw candidate passages with the different predicate labels for the spans in the passages. And then we do the answer passage selection. We built this answer passage selection model with additional fine-grained metadata encoding. Firstly, how do we generate the decorated passages? We need to first obtain all the metadata pairs from the URL that the candidate passage appears in. Then for each metadata pair, the textual object and predicate pair, we employ a similarity function to decorate the candidate answer passages. For example, here, for this candidate passage, after this decoration process, we know that tilapia fillet and salt and pepper, the two spans, should be ingredients. And secondly, we built our answer passage selection model with additional fine-grained metadata encoding. So the basic encoding contains the contextualized word embeddings, and secondly, the aligned query embeddings. And most importantly, in this work, we also add this fine-grained embedding for the metadata predicates. And firstly, for example, for the example recipe to cook time a decorated span, we first encode the root embedding, the recipe, and also the cook time, which is a property embedding. Beyond these two basic encodings, we also add the path, or say the relation embedding, because cook time might also fall under other roots. So to make this relation more specific, it will be more fine-grained. And after this encoding for the passage and question, we in the output layer, we calculate the is-selected score for each passage. And next, I will introduce our experimental results. In the evaluation, we did the evaluation on the passage selection task of MS Markov dataset, which was published in 2016. And we also did the evaluation on the subset of MS Markov, which explicitly contain the questions regarding recipes. And we show the statistics for the training, development, and test sets in this table. As for the evaluation metrics, we report the precision as 1 and mean reciprocal rank for the performance of each question answering model. And here, in this table, we present the performance for the baselines and our systems. We compare to a number of previously published baselines, including SNet, and directly selecting the first passage, as well as a neural passage selector, which is NPS. And for B, NPS meaning our model which uses a basic encoding for the metadata information. And as for FNPS, it stands for fine-grained embedding for neural passage selection. And from this table, we see that by encoding the additional fine-grained embedding information from the metadata, it consistently improves over the baselines, which does not include this information. And as for the fine-grained encoding of the metadata predicates, it gives further improvements as compared to the basic encoding of the metadata information. And to further understand these improvements provided by metadata information, we selected a bunch of areas which are with a bigger proportion of metadata, which are book, medical, person, organization, and reviews. So in the second column, we see that for NPS, it achieves like nearly 30% accuracy for PS1, while after the fine-grained encoding for the metadata information, it provides a bigger improvements, like from 3% to over 5%. It also proves that this metadata is really helping for these domains. And to conclude, in this paper, we propose to incorporate metadata information via fine-grained embedding of the predicates. And we describe methods for obtaining the metadata and decorating the passages, as well as the fine-grained encoding for leveraging them. And secondly, our findings also provide motivation for the website builders to do more annotations for their website pages with the schema.org markup. And thank you for listening. That's my presentation. If you want more details, please refer to our paper.